This is going to be a description of our first real programming assignment. So the other ones have been kind of optional and some people have been opting out, but this one is going to count for a grade and it's fairly challenging. You're going to have 2 weeks to do it, and I expect to be helping you a lot. So if you get stuck, please don't try to go it on your own. So basically what we're going to be talking about is the idea of a well-formed formula, and that's usually abbreviated WFF, not to be confused with the Wrestling Association or the Wildlife Foundation, or the acronym for a state of confusion that involves the use of serious vulgarity. So a well-formed formula is something that comes up in the study of formal logic, which we are going to be sort of, looking at a little bit kind of tangentially in a week or so. But you can really understand it in terms of arithmetic too. So without knowing any logic at all, the idea of a well-formed formula is, certain expressions make sense, like 3 plus 6 times 7 plus 8. So that's sort of a grammatically correct mathematical statement. But something like 3 plus plus, that's meaningless. So you can't ask a kid what that means and expect them to give you a reasonable answer. And there are a lot more non-well-formed formulas than there are well-formed formulas, like 2 parentheses in a row with 3 inside, and then that's incomplete. It's just wrong. And what we're going to do is, I guess maybe we're actually going to be working with logic instead of arithmetic, so maybe I should say a little bit about that. And the kind of logic that we're going to be doing is called Sentential Logic, sometimes called predicate calculus. So these are terms that you could Google if you want to know more about these things. And we're going to have just the idea is that you have a certain set of primitive sentences, like A, and you should understand A as a symbol. So it's just, the symbol or the character A. And the idea in sentential logic is that this could stand for many things, like maybe A stands for the proposition that a bird is on the Empire State Building or something, which is either true or false. And so you have a bunch of these primitive symbols. So for primitive symbols, I'm going to use just the capital Roman letters. So just to give an example of how these things could actually mean something, let's say that A has been assigned the meaning a bird is on the Empire State Building, and the symbol B has been assigned the meaning violets are, I don't know, blue, let's say. Now, from these primitive symbols, so that A is a primitive symbol, B is a primitive symbol, you can make non-primitive logical claims like A plus B in parentheses. Okay, so this is a new logical statement, and it's an example of a well-formed one. And what this is saying in the notation that we're going to be using is A or B. So in other words, plus stands for or. And the fancy word for or is disjunction. So A plus B is a sentence, a logical sentence, and its form is a disjunction, and it's saying that A is true or B is true. And so this assertion, A is true or B is true, well, is it? Actually, it depends on whether a bird is on the Empire State Building or not. See, B is definitely false, but A could be true or false. I don't know if it's true or false right now. Sometimes it's true, sometimes it's false. But this is something that could either be true or false. And so I just introduced the plus operator, which is going to stand for disjunction or. There are two other operators we are going to need, and one of them is the AND operator, which we are going to represent by using the multiplication symbol, or on the computer keyboard, just the Shift 8, the asterisk. So this is a well-formed formula that's true if and only if A is true and B is true. So again, well, actually, this is definitely false because B is false. So A and B must be false if B is false. And this is, I know that, I don't know, maybe it takes a while to get used to that, but this is just the sort of, weird things that you get used to when you start studying logic if you haven't done it before. Actually, these issues of truth and falsity and meaning are completely outside the scope of the assignment. We're really going to be studying proper grammar, and it doesn't really matter what the meaning of the symbols is. We just have to make sure that the statements have proper grammar so that they don't look like this or like B star star C or something. These are supposed to be meaningless. Well, they are meaningless. They're non-well-formed formulas. So we're going to be writing a program to recognize well-formed formulas, and you don't need to understand predicate logic to be able to do it. In fact, the meaning of these formulas doesn't even have to have anything to do with predicate logic. You could interpret them just as about algebra or something if you want to. We just want to be able to recognize the correct grammar. There's one more operator. I'm sorry, I'm doing this stuff kind of out of order. So this you can, if you want to think of it as meaning something, which of course you do because you're a human being, and that's why I'm saying all these things. The star means and for negation we are going to use the negative sign from the keyboard. So this is negation. So and I'm going to put it in parentheses. So this is a well-formed formula, and it's true if and only if A is not true, which again depends on whether the stupid bird actually is on the Empire State Building or not. But not B is definitely true because B is definitely false. Isn't it? You guys maybe have been thinking that I'm insane the whole time saying that B is false. Violets are violet. God, I'm such an idiot. Okay, so it depends on how colorblind you are. God, this is like the worst explanation of all time. So I've been considering B a false statement because violets are violet, and I'm considering that a distinct color from blue. And this is an idiotic thing for me to have done because there's actually an English idiom which is violets are blue. So I'm a dumbass, that's all I can tell you. So let me go on to give some examples of well-formed formulas, and then I'll give the formal definition. So we've already seen, A is a well-formed formula, B is a well-formed formula, C is a well-formed formula, and these are all the primitives. If we were doing serious logic, we would define, probably infinitely many primitive symbols, but I'm just going to use the 26 capital Roman letters. Now, from these primitives you can make more, and we've sort of informally done that. So from any primitive you can form its negation of a primitive. And so this is a well-formed formula, and well-formed formulas have a recursive structure. So if you have a well-formed formula like this, you can always make another well-formed formula out of it. So this is just the negation of that well-formed formula. And if I take this well-formed formula, I can, or I don't know, let's take one of the primitive ones like b, and let's say b and not a. Okay, and this is a well-formed formula, and they sort of build up like this. So all of them have a certain form, and hopefully when I give the rules right now explicitly, you'll see the principle that simplifies everything and makes it easy to understand. So let's give the formal definition of a well-formed formula. Okay, so the formal definition is that I'm going to number these, A, B, C, Z are well-formed formulas. So these are the primitive ones. And so now this is a rule for making another well-formed formula out of an existing one. So if, and I'm going to use a Greek letter here because I've already used up all the Roman letters. I hope that doesn't make it seem too confusing. So if phi, that's Greek letter phi, is a well-formed formula, then not phi, in parentheses, is a well-formed formula. Okay. So this just says that if something is a well-formed formula, then so is its negation. And I have another rule. It's the rule corresponding to plus and times. If phi and psi are well-formed formulas, then phi or psi in parentheses and phi and psi in parentheses are well-formed formulas. Okay, so now we have the rule for sort of generating them, and that's kind of what I was doing up here when I was playing around. So let's explore this a little bit more to help build up your intuitions about things if you've never seen anything like this before. So I'm just going to build a pretty complicated well-formed formula. I wish I had thought of one beforehand. So I have some here, and maybe I'll just copy this one. This one is this always on top thing is awesome. I don't know why they don't do that in Windows, but so I'm just going to copy this well-formed formula that I have in row 6 here. So it is A and B, or C and D. Okay, so it's not too complicated. What I'm trying to illustrate here is that all well-formed formulas have a recursive structure. So what that means is this is just kind of using the definition that we just saw backwards. So this is, sort of bottom up, but we can go top down, and we can say, well, if I know that this is a well-formed formula, then it must be a formula that has one of 3 forms. It must either be a primitive, that means a capital Roman letter, or it has to be the negation of some other well-formed formula, or it has to be the disjunction or the conjunction of 2 well-formed formulas. So as human beings, it's not too hard to recognize that the form of this well-formed formula is that it's a disjunction of the well-formed formula A and B and another well-formed formula C and D. Okay. Now these are well-formed formulas, so they must have some form, and it's easy to see that the form of both of these is conjunction. So this is a conjunction of the primitive A and the primitive b, and the primitive c, and the primitive d. Okay, so this is when you write your program to determine whether or not a formula is a well-formed formula. It's probably going to involve a recursive function, and a recursive function is a function that calls itself. So just to give an example of I guess there's a lot to explain here, isn't there? So let's give an example of a recursive function, and let's write it in Python. And let's let it be just the length of a string. And of course Python can do this in one line, so there's no reason to write this function, but just to illustrate things. So I want to write a recursive function to figure out the length of the string s. So one thing I might do is say, if, I'm going to assume it's a string. You know, you could put in a type check or something, but I'll just assume it's a string. If s equals the empty string, then return 0. Okay. So this is sort of the base case, so all recursions have a base case, which ultimately gets called. And in recognizing well-formed formulas, the base case is when you get down to primitives. Otherwise, then s must have some characters in it, so we'll return 1 plus the slice of s that goes up to, but does not include its last element. Right? So just to give and that's it, it's done. So just to give an example how this is working, if I call strlen on AB, let's just call it on AB, then what does it do? It's going to return 1 plus strlen A, and this is going to return 1 plus strlen of the empty string, and this is just a number which is 1 plus 0. So it'll return, this is an expansion, so this is really 1 plus the result of this, which is 1 plus 0. So the final thing it'll return is 2, which is correct. Okay, so that's just an example of how a well-formed formula works, and this function that you're trying to write, it's basically, first you have to take the string that you're given and try to recognize it, if possible, as one of the 3 possible combinations of other well-formed formulas, and then call itself. So if I were trying to do, is well-formed formula, and I had somebody had given me some input which is of the form phi or psi, what I would do is, basically things are going to be more complicated than this, but in principle, all you have to do is sort of return is WFF phi and is WFF psi. And similarly for the other cases, so if you can recognize the negation, then it's a W. So if I call is well-formed formula, and I know that the input is of the form not psi, this is not supposed to be syntactically correct Python, I'm just trying to illustrate the idea, then here you would return is well-formed formula psi. So this is the negation of some chunk of letters, and so it is well-formed formula provided that phi is a well-formed formula. So you just check is well-formed formula phi, and similarly is well-formed formula phi and psi, you just have to return. Actually, it works just like the disjunction is well-formed formula phi and is well-formed formula psi. So this is what I mean by recursive. You know, this is actually going to have to be something that is an actual legitimate string in ASCII, and I have some examples here. So these are all well-formed formulas. So A obviously is a primitive, and this is the negation of a primitive, and this is the disjunction of the negation of a primitive and another primitive, B. This is the disjunction of two primitives. This is the conjunction of two primitives. We've already looked at this one. This one is the conjunction of the negation of a primitive with the disjunction of two other primitives. This one is the double negation of a single primitive A. And this is the disjunction of A with the disjunction of A and B. And this one is the negation of the previous one. Okay. So whether or not something is a well-formed formula is a really precise idea. So anytime a computer can decide something like this, you know, it's going to be sort of really exactly specified what qualifies and what doesn't. So here, this file contains non-examples. So each one of these fails to be a well-formed formula for some reason. They all have flaws. And some of them look fine. You know, they look like arithmetical or logical statements that a human being might write down, because we could, you know, understand that this, what the meaning is, or figure out what the intention was, or what the person who wrote it must mean. But the computer is going to fail to recognize it as a well-formed formula because it doesn't satisfy, or it can't be realized as something that satisfies these very specific rules, these three formal rules. So these are precisely the well-formed formulas. So A in parentheses fails to be a well-formed formula because there's no way to realize it using these rules. So for instance, A is in a set of outer parentheses. So how did it get to be in those parentheses? Well, either it must be a disjunction, a conjunction, or a negation. But you can see that it's none of those. It's itself a primitive, and so that means that it's not a well-formed formula. Now, you could say, but that should be a well-formed formula, Hunter. You need to enrich your definition. So yeah, okay, you know, maybe we could model reality better if we made this more complex, but we're keeping it simple so the program that we're trying to write will be simple. We don't want it to be any more complicated than this. So 2 fails to be a well-formed formula. Why is that? It's because you can see from the definition that the only well-formed formulas that aren't wrapped up in parentheses are the primitives. And this one, number 3, fails to be a well-formed formula because there's a parentheses mismatch. So see how there's one left parenthesis but 2 right parentheses. So in any well-formed formula there have to be equal numbers of left and right parentheses. So you can make up stories for all of these about why they're wrong. You know, some of these are obviously wrong. Nothing is obviously wrong. So all of these are negative examples, and I'm going to give you the file containing the positive examples and the file containing the negative examples, and you can use those to test your work. And I just did the project myself, and it's pretty tricky, and I used those files to test my own work. And so here I imported my work as a module. This is really easy to do. I just did it so that I didn't, you know, reveal the answer while I was explaining how everything works. So my file is what is it? It's wff_wtf.py, and to import it as a module, it just has to be in the same folder as as the thing that's doing the importing. And I'm importing it as WFF. And so first I'm opening the positive examples and stripping them and stuff. And the functions that I have inside my module are, just to give sort of a hint, these, I don't know if you can read this. If your resolution is coarse, you might not be able to read these. So these are some functions that I have defined that are part of my solution. One of them is atomic, that checks to see if it's an atomic well-formed formula. This is WFF, which is, is a woof. And that one's pretty complicated. That's the top level function that calls some of these other functions as helper functions. This function is called next chunk. And that's an important function, so maybe I can so I don't know if you can see this here. Can I make that bigger? I think I can. Just give me one sec. What is that thing called? The object inspector. I just want to boost up the font size. Alright, so this is the documentation, or just the comments that I put in my own function. So this returns the highest level block of match parentheses and the index where it ends, and also the starting index. So this is actually what would happen. By the time I call my next chunk function, I've already stripped off the outer parentheses, if there are any, and okay, so this, what is it saying? You know what? Why this looks weird? Sorry, it's because it's ignoring the new line in my comments. So let me pause the video and try to fix that. Okay, this is a little bit better. So just ignore the zero. The zero is just saying start at the start of the string. So what next chunk does for me is it sort of extracts it recognizes that maybe it's of the form something disjunct something else, and it just returns the first chunk. And so if I run it again on what's left, then I get, the next chunk, and that's how I'm writing code to parse these things. Here's another example of what it returns. So if you give it the outer parentheses have already been stripped off. If you give it this conjunction, it finds the first piece of the conjunction, and it returns the index at which it ends. So frequently, I guess, one reason I wrote this is because frequently this is going to be the index of the operator. So can you see here that the index of plus is 0, 1, 2, 3, 4, 5? So I use that to sort of extract the index of the operator. You can't just do a string search to look for plus or times or something, because you can see that you're going to get, if you search for plus, there might be another plus, not just this one, but the first plus might occur somewhere beside. It might not be the thing that everything hinges on. It might be part of a sub-formula. So you have to do something more sophisticated than just string search. And the output, if you look at the output here, so first I run my isWoof function on all the positive examples, and so it should say true every time, and it does right here. And it didn't, the first 35 times that I ran it. I made a lot of mistakes and had to figure out how things worked. I have it set up so that it outputs a lot of debug, and if you've never heard the word debug before, that's just output that your program generates to help you figure out why it's not working. And it's always not working when you first write a program. I don't think any human being has ever written a working program that did not have a bug in it before it was debugged. So I wrote this stuff to help me figure out what was going wrong back when things were going wrong, or things were going wrong that I was aware of. So this just shows you how I was verifying to myself that the recursion was working correctly. So when I'm checking this well-formed formula, it should be that it has to examine A to determine if A is a well-formed formula. And here it should recurse on the two things that are being disjuncted, and the two things that are being disjuncted are this and that. Here it should recurse on the thing that's being negated, which is A. Here it should recurse on the two things that are being disjuncted. So can we see sort of an interesting one, I guess? If you look at this line, and you look at the next few lines, then you can see how things are unfurling. So this is a conjunction of two things, and so it undoes the conjunction and looks at each of the pieces individually, and so it considers this, it recognizes that that's a negation of something, and then recursively checks whether that is a well-formed formula, but that's a primitive. And notice that all these recursions end in the case where you're considering a primitive. That's going to be the base case of the recursion. And so similarly for this part is the second part of figuring out this first one, because it's the second, this is the second conjunct in this expression. And from here it has to look at B and C, and everything works out. And yeah, so pause the video or something and look at those others if you want. So it says that all of these are true, and that line is the output that comes from line 14 here as a result of the map statement. Now I do the same thing for the negative examples, and something should go wrong for all the negative examples. Weirdly, or kind of hilariously, getting it to return false for the negative examples is, I found, harder than getting it to return true for the positive examples. You know, you could write a function that just returns true no matter what, and that would work great on the positive examples, but not so well on the negative examples. So it has to, you know, correctly identify both ways. I'm sorry, I'm not sure what's going on here. So here it just says parse failed for all of these things. And I have my, you can probably do it some other way, but I realize one nice thing about Python is that you can set up the parse as a try except block, and that saves you the trouble of checking for some weird cases. You know, you just try to do what you think should be true if it's a well-formed formula. If something blows up, it's sort of the formula's fault, and that throws an exception. And then if you do get an exception, then you just say parse failed, answer is false. And that's what's going on for all of these. So I don't know how much more there is to say about this. Whoop, that's the code. Shoot. Am I going to have to destroy this video? What did I just show you? You're going to be able to rewind and look at it anyway, so I might as well be honest. Is that too much for you to see? Okay, so I don't know. We'll just call that a hint. So you get a little hint. Sorry about that. Sorry about the hint. And I guess I'm going to stop the video. I know if you've never seen formal logic before, you've never seen recursive functions before, then this is going to be a challenge. I intend for it to be a challenge. Some people are going to be able to easily do this. Other people are going to have a hard time. Still, other people may work hard and not succeed at all. And don't worry. I want you to work hard, but I also don't want you to lose your hair and get, you know, some kind of immune system disorder from worrying too much about writing this program. So just give it a shot, try to get started, and write me an email if you run into problems. Oh, by the way, it's easiest for me if you keep your work in your Dropbox folder. Don't email it to me, just, you know, say that it's in the Dropbox folder, and I'll just go look in the folder on my computer. It's sort of the most convenient thing for me. So talk to you later.